Okay, Assalamu alaikum. So we'll start our first meeting. The meeting number 6. So in this meeting, we'll see all about algorithms. Okay, so it is the last meeting in the block 2. Okay, so it is not uncommon to read articles with titles like Google's, for example, algorithm for ranking web pages, or Facebook's algorithm for curating news stories. But our civilization is increasingly reliant on algorithms. As you know, everything in our lives will pursue an algorithm. Therefore, it is worth learning more about exactly what they are and about some of their strengths and weaknesses. So you have in this meeting, you have to learn that an algorithm may describe how a problem can be solved by a computer. However, as we discussed in this part, the concept of an algorithm is more general than that, okay? Okay, let's start by this simple example of algorithm. So simply, an algorithm is a step-by-step guide to completing a particular task, okay? So this is what does it mean, an algorithm? It is simply a step-by-step guide, okay? Go to this point, turn 50 degrees, okay, etc. Okay, to complete a particular task. So you have a particular task that need to be completed, okay, and you will follow a step-by-step guide to achieve these particular tasks. Okay, many of our everyday activities follow an underlying algorithm, okay? So for example, here an algorithm for brushing teeth. In fact, when you brush your teeth, you will do some algorithm, okay? You will apply some algorithm for doing that, okay? So in the first, you will turn on your tap, okay? With the toothbrush. Fill glass with water, turn off tap, apply toothpaste to brush your teeth, okay? Spit out your toothpaste, okay, etc. Okay, so this is the step in which by these steps you will brush your teeth, okay? So in fact it is an algorithm, it is step by step. How you can write an algorithm? No, you will write this step. You will write it in okay, in any Word, okay, in any Word program, okay, the algorithm, and after that, this algorithm will be implemented, okay. So in this course, we will implement all algorithms in OU build, but you can the same algorithm can be implemented in any other programming language, okay. Do you understand me? Are you with me? Where are you? So this is the importance of the algorithm. The algorithm will help you to understand, to resolve, okay, to achieve the task required by the program, okay. After that, these steps can be implemented in OU build, can be implemented with Python, can be implemented with Java, okay, etc. Whatever the language, it will follow the same, okay, the same algorithm. Still, you have some differences in the syntax, okay, of the programming language, okay, but the same results, you will have the same results, you will pursue the same steps, okay? You will implement the same algorithm, okay? So another example of obviously algorithmic are the recipes, okay? When you prepare a cake or when you prepare whatever the meal, okay? So you will follow some steps, okay? And this is an algorithm. It is called a step-by-step algorithm. So you will grease, for example, loaf tin, you will melt 200 gram of butter, you will add 3 whisked eggs, etc. Okay, all these steps are called an algorithm. Okay, it is the algorithm to do a beetroot, for example, cake, or to make a beetroot cake. Okay, so everything in our lives, okay, will follow an algorithm to achieve the task. To do the required task, you need to follow some steps. Okay, this is what does it mean, algorithm. Okay, look now at the fundamentals of algorithms. So how we can tell that this is a good algorithm or not. A well-written algorithm for a program can be implemented in a variety of programming languages. Okay, it is not related to the language. It is not related to the language. It is related to the task itself, to the steps to do this task. Okay, so this is a well-written algorithm. The implementations of an algorithm in different languages, of course, all look different, but they all share the fundamental features described by the algorithm, okay? All the fundamental features of your algorithm will be displayed, okay? Will be the same, okay? Understanding these fundamental algorithmic features can help you more readily understand programs, even in languages that are new to you. Okay, so when you know these fundamental algorithmic features, okay, how to understand these algorithms, you can understand all the programs, even when you provide the programming language. You don't know this programming language, okay? So even in languages that are new to you, okay, it will not be difficult, okay? Why? Because you already understand the fundamental algorithmic features, okay? Okay, so what is the algorithm? What is the algorithm definitions now? An algorithm is a set of step-by-step instructions. Now we have here instructions step-by-step to complete a particular task, okay? It can be applied for the algorithm, computing algorithm, for daily algorithm, for daily lives algorithm, okay? Whatever the field, okay? But an algorithm is a set of step-by-step instructions to complete a particular task, okay? So similarity between everyday algorithms and those used for programs. Now we will distinguish between, and we will see the similarities and the differences between everyday algorithms. What are the everyday algorithms? When you wake up, when you brush your teeth, when you prepare your breakfast, when you go to your work or to your school, etc., to your university, etc. Okay, so these are the everyday algorithms. Okay, and those used for programs, for computers. Okay, both have set of instructions. So we are agree that both of them will use a set of instructions. Okay, there are some steps to follow. Okay, so the style of instruction, yes, it is recorded. So the style of instruction in each case is very different. Okay, the style, okay, but both of them will have instructions, and both complete in a finite amount of time. Okay, so here we have a finite amount of time. After 1 hour, after 5 minutes, after 2 hours, after 24 hours, okay, this algorithm will finish, okay? So we have some deadline, we have some finite amount of time. So there are some processes that go on indefinitely, but we don't consider them amongst the algorithms we analyze in this part, okay? So just like a recipe, an algorithm must stop. It needs not be quick. It may take years to generate an answer, but it must eventually finish, okay? Eventually will finish, okay? You cannot see my slides, but I have shared with you. Do you see the slides? Okay, now you can. And now, can you see now? Can you see? Okay. Okay, so this is the difference between the similarities between the everyday algorithms and those used for programs. Now the differences. Tell me what are the differences between the everyday algorithms? What the differences between everyday algorithms and those used for programs? What is the difference now? So now the difference is the everyday algorithms are imprecise, okay? They are not accurate and may omit an instruction relying on humans' previous experience, okay? Or general knowledge. For example, we can tap on the open the water. After that, we can prepare my brush teeth, okay? We can do, for example, in the cake, we can begin by the eggs, okay? We will mix the eggs. After that, we will add some sugar, some flavors, okay, etc. Okay, so these steps can be changed, can be one instruction be in front the others, okay, begin after the okay, it is related to the human previous experience, okay, or general knowledge. I know that when I mix the egg with sugar, it will be better, okay, so I will begin by this step. I will not add some milk or some butter for this cake until I have a good mixture, okay, of the egg and the sugar, for example, okay. So this is for this everyday algorithm. It can be relying on human previous experience, on a general knowledge, okay. So for example, a recipe may sit bake for 45 minutes at 180 degrees Celsius, okay, without giving explicit instruction to turn the oven on and off, for example, okay. But algorithms for programs must be precise, must be self-contained. What does it mean, self-contained? What does it mean? What does it mean, self-contained? Self-contained means that you need your algorithm must contain all the instructions required to solve. Yeah, good, independent. All the instructions that required to solve the problem, okay? And those instructions must be unambiguous, okay? It must be clearer, okay? Because computer cannot deal with omission or imprecision, okay? Computer is not human. He can understand that when you don't for example, show that you need to turn on the oven or to turn off the oven at the end of this receive. Okay, the computer cannot understand that. Okay, you need to show all about to the computer. Okay, cannot deal with omission or with imprecision. Okay, so this is the main difference between the algorithm, the everyday algorithms, and those used for programs. Okay, so the algorithms used for program must be precise, must be self-contained. Okay, and be sure about that, self-contained. So whenever you need, for example, to test a list, so you need to create this list. Okay, to do some test on this list, or to fill this list when you are asked. Okay, and in implementing their own algorithm, so a programmer may clarify the ambiguous and fill in missing steps, and thereby arrive at a working program. Okay, so this is the role of a programmer. What is the role of a programmer? Okay, when you, for example, implement their algorithms, the programmer, okay, need to clarify all the ambiguity. If there are any ambiguity, if there are any missing in the steps, okay, it will be clarified. It will be not ambiguous. Okay, and one advantage of algorithms is that once an algorithm is written down, it can often be reused over and over by other people wanting to solve the same problem in different programming languages. Okay, so this is one advantage of the algorithm. Okay, we can use, for example, you have an algorithm to fill a list. Okay, so whenever you need to fill a list, you will use the same algorithm. You don't need to do another algorithm for that, or you need to show, or you need to show the contents of a list, or you need to get a small for one list, the smallest item, the biggest item. Okay, all these algorithms can be reused several times. Okay, why? Because it is there are some common used algorithms in many different programs. Okay, so it can be reused once it is well written. Okay, it is well written, and it is clearer. Okay, so the algorithm can now be defined more precisely as, so look now at the more sophisticated algorithm definition. So it is a set of unambiguous, clearer, self-contained, step-by-step instructions guaranteed to complete a particular task in a finite amount of time. Okay, so I think all about the algorithm is now is here in this definition. Okay, so it is a set of ambiguous. Okay, there are no ambiguity, there are no missing steps, there are no misunderstanding. Okay, self-contained, all instructions, all that you need in this algorithm, it will be contained. Okay, step-by-step instructions, okay, that guarantee that help you to complete a particular task in a finite amount of time. So you have some finite amount of time that this algorithm should work. Okay, refinement now. Ambiguity is a real problem for algorithms designed for programs. Ambiguity, what does it mean, ambiguity? الغموض. Okay, so ambiguity is a real problem for the algorithms. When you read, okay, this algorithm, you don't understand if he mean by this instruction that he need to, for example, assign the smallest to this variable, or just for example, to compute the smallest. Okay, so there are some ambiguity, some things that is not clear. Okay, that you cannot, that you need to guess. Okay, it is not clear. Okay. Okay, so ambiguity can be overcome by breaking instructions down into smaller steps to clarify the order of individual actions. Okay, so when you have some ambiguity in your program, so you need to break down your instructions, okay, into smaller steps. Okay, when you are asked to do, for example, to compute the smallest, okay, compute the smallest, in this phrase there are several steps. Okay, so we can take this part, we can refine this part, we can break down this step into smaller steps. Okay, so this process is sometimes called refinement or decomposition. Okay, is it clear what does it mean, refinement or decomposition? For example, we may start by an instruction like deduct rounded discount amount from the total price. Okay. Okay, so you need now, if you need to refine this deduct rounded discount amount from the total price, so we will calculate the discount, we will round this discount, and we will reduce this total price by discount. So we will have the total. So from this phrase, okay, this instruction can be refined into these, or can be broke down, okay, into smaller steps, into 3 smaller steps here. Okay, so do you understand what does it mean? When I told you that, for example, compute the smallest, okay, or show the smallest number in the list. Okay, so it can be refined by assign the first item of the list to smallest, go through this list and compare if the item, okay, in some position is greater is lower than the smallest, so the smallest will be this item. Okay, until we achieve the length or the end of this list, for example. Okay, so by this way this instruction can be broken down, can be refined, can be decomposed. Okay. Okay, now look at the fundamental features of computer programs. So computer programs vary in purpose and complexity. Okay, so there are many purpose for computer programs and there are many complexity programs. Okay, the complexity of the program differ from one program to another. So as well as in the language they are written in, we have several language, we have several purposes, we have several complexity degree for these computer programs. So for example, the Google search engine is a computer program. The camera face detection software, the aircraft flight control software, the online UK income tax calculator, all these programs differs from purpose, okay, from complexity, and from the language they are written in. Okay, so the many tasks each of these programs perform are based on algorithms, but all these programs will have or will are implemented, okay, using their algorithms. That is, they follow precise, finite, step-by-step instructions. Okay, so all these tasks, even if they are varied, okay, in purpose, in complexity, in language that they are written in, okay, but they are based on algorithms. So they will follow, they are precise, they are finite, they are step-by-step instructions. So the algorithms for these and all other computer programs are built around 4 simple ideas. Okay, so you need to understand the simple ideas for this algorithm. What are these idea? Okay, so you need in the first to define your inputs and your outputs. Okay, so for each program you will have input and output. You can have some programs without input, you can have some programs without output, okay? But you will use some input and output inside this calculation, okay? There are some sequences of instructions, sure, okay? There are some repetition of instructions and selection of instructions. So you need to understand all these, what are the inputs, what are the outputs, what are the sequence of these instructions, the repetition and the selection, okay? So by combining these 4 ideas in different way, you can create an algorithm, okay? So you can understand if there are some selection, if there are some repetition, if there are some sequential blocks, okay? These and what are these inputs, what are the outputs of this program, all these features you need to understand, okay? Okay, let's begin now by the inputs and the outputs. So it is possible to imagine someone writing an algorithm that takes no external input, that always produces the same output, okay? It can be, but as a rule, an algorithm that always produces the same output would be of little use, okay? When you have the same output, okay, for all these for the programs, okay, and it is not related to some external input, okay, it will be of little use, okay, because it is not customable, okay. We need some customable programs, okay, that change with different inputs, okay. So we need algorithms to be able to start with different data inputs and to produce output that varies according to the input data, okay? When you have, for example, the algorithm for example, printing the smallest item of a list, okay? When these program have as an input the list, okay, and as has an output as the smallest, okay. So this program can be reusable, okay, can be a grid of use, okay. Why? Because once I have a list and I need to calculate or to compute the smallest, I will use this program. But when there are no list, okay, so the list is already like a constant, okay, it is related only to this list, okay, and it will show only the smallest of this list, okay. So I cannot use this list, it cannot be customable. I cannot change the list, okay, so it will be of little use, this program. So this enables algorithms to be general purpose problem solving tools, providing different solutions in different situations, okay. So for example, consider the following algorithm SNP, which requires 2 pieces of input data from the user and outputs 1 piece of data. So you will input the first number, the second number, and it will display the mean, okay. So this program, okay, we can in OU build, you may implement this as in figure 1, for example. So I will ask you to give me the first name. I will store this your answer to the variable or to the data number one. I will ask you again to give me a second number, and I will store your answer in number 2. After that, I will define the variable mean, okay, which will be the average of these 2 variables, and I will say the mean is the variable mean. Okay, so this is one implementation for this algorithm. Okay, sorry, for this algorithm. Another, we can implement the algorithm in Python. Follows the same basic pattern. Okay, the same steps. I will ask you to give me the number 1 by Python. I will enter your first number. Number 2, enter your second number, and I will calculate the mean and print the mean to the user. Okay, so it is the same algorithm with the same steps. Okay, but the difference here is the programming language. Okay, not all input data for an algorithm comes from the user. There are some data that an algorithm needs may come from the environment in which the program runs. For example, consider the following simple algorithm snippet. Okay, so tell the user what the last year was. Okay, so you need to have some built-in data. Okay, there are some built-in data providing the current date and time. Okay, and this sort of data can be used by an algorithm. So I will get this year and I will subtract this year by 1 and display the last year, for example. Okay, so there are some data that can be, not only all the data will be given or comes from the users, it can be from the built-in. There are some built-in data in the computer. Okay, so I can use this built-in, like the data, the date, like the date, the years. Okay, all this thing. Okay, I can or the place or whatever. Okay, so I can have some data from the computer. Okay. Okay, move now to the sequence, repetition, and selection. So now suppose a cola merchant, okay, is giving loyalty points for their customers according to the following algorithm. So look here, you will repeat 6 times, input box price, add box price to total price. And if the total, okay, so this is ended here because the indentation, okay, is ended. So if here it is not inside the repeat, okay, so this is the indentation, how to write your program to understand. Okay, make the program readable. Okay, more readable. Okay, clear. So if total price now is greater than 5,000 of pounds, then calculate the loyalty points as 5% of the total price, rounded to the nearest whole number, and tell the user the loyalty points earned. Else, tell the user there is no loyalty points earned. Okay, so here we have some sequential. Okay, so I will repeat, and after that I will calculate the loyalty, or I will have an idea about the loyalty. Okay, so from top to down, except where an instruction involves repetition or selection. Okay, so this repetition, in this repetition we have not sequential. Okay, we need to go, okay, to repeat these instructions. Okay, and this is the this selection. So the algorithm starts with the repetition instruction. This is the repetition instructions. These instructs the algorithm to repeatedly iterate through the indented sequence of actions, the loop body, in order 6 times. So the actions that are repeated are get the box price from the user and add the box price to the total price. Okay, so it will have 6 times to do that. The way the repetition instruction is set out within the algorithm, with the condition at the top and the actions indented underneath, emphasizes the connection between them. Okay, so you need to understand from the indentation what are the instructions that are within this repetition. Okay, are you with me? Is it clear? Okay. Okay, thank you. So this is what, okay, so now this particular sort of repetition instruction corresponds to a fixed loop. Okay, so here we have a fixed loop instruction that corresponds to a fixed loop that repeats a sequence of actions a fixed number of times. So you have here 6 times. You will ask the user to enter the price of the box, okay, and you will calculate the total price. So in all, fixed loop are implemented with the block repeat, okay, and the number of times as in the figure, okay, is shown in the figure. Okay, so you will set the total price to 0. You will repeat 6 times. Ask the user to enter the box price. Set the box price to answer, okay, and change total price by box price, okay, or add, okay. In Python, an equivalent code can be implemented using something known as for loop, okay. So in Python, you will use for the for loop. So you set the total price equal to 0, and for item in range 6, okay, it means that item will go from 0 from 1 to 6, okay. So the box price will equal to the input in the box price, and the total price will be equal to the total price plus float box price, okay. So this is the implementation of the same program, but with different language, programming language, okay. The same algorithm, but with different programming language. Okay, so here Python doesn't have a direct equivalent of repeat until, okay. So if something called a while loop, it has something called a while loop, which could be used to implement the same algorithm. Okay, so as you know, there are some algorithms that contains the while, okay. In all you build, we don't have the while loop, okay. We have repeat until, okay. It is the same as while, okay. So it is when you use the or you build, so you will use the repeat until, and in Python, for example, you will use while, okay. So you will here define the total price by 0. The box count is equal to 0 because now we need to calculate the box okay count. While box count is lower than 6, I will ask you to give me the box price, and I will calculate the total price by adding the box price to the already total price, and I will increment the box count by 1, okay. So here the while loop repeats while a particular condition holds. Here, while this condition holds, okay, it will be repeated, but in repeat until, we will repeat until this condition is met, okay. Therefore, the while loop condition must be different from that needed for the or you will repeat until, which repeats until its condition holds, okay, which repeats until each condition holds, okay. So here is an algorithm for the program to count down from 100, for example. So set it to 100, repeat until I is less than 1, and tell the user the value of I, decrease I by 1, until the user blast off is finished, okay, here at the end. So what change could be made to the condition in order to please repeat until with repeat while? Look now here we have used repeat until I less than 1. I need to use repeat while, like in Python, okay? So how we can use it? How we can change the condition here? Give me your answers. You cannot see the slide. Why? I don't make any changes. It is perhaps. Now you can see it. Okay. So look now. Here you have an algorithm for a program to count down from 100. Okay. So in the first, we use repeat until. So we will repeat until I reach 1. Okay. So I will begin by 100 and I will decrease I by 1 until I reach I equal to 1. Okay. So what changes now could be made to the condition in order to replace repeat until with repeat while? Now repeat while I is lower than 1. Okay. Is greater than 1. Repeat until I is greater than 1. Yes or no? So I will repeat while I is greater than or equal to 1. I will, okay, repeat while is greater than 0. Okay, here strictly greater than 0. Here greater or equal. Okay, so here I repeat while I greater equal I, here I 1. Here I is greater than 0. Okay. Is it clear what is the difference between until and while? Clear? No. I will repeat while this number is greater than 1 because it is not, we don't reach the 1. Okay. Okay. Back to our collaboration now algorithm. After completing the repetition instruction now, the algorithm moves on the following selection instruction. He will calculate if the this customer, okay, will benefit from loyalty or no. Okay, so if the total price now is greater than 5,000 pounds, okay, then calculate the loyalty point as 5% of the total price, okay, rounded to the nearest whole number, okay, and tell the user the loyalty point earned. And else, what does it mean? Else it means that the total price is less than 5,000 pounds, okay. So there is an if then else selection instruction here. So here we have used the if else, okay. This selection part starts by considering the condition total price is greater than 5,000 pounds. So if the condition holds, then the if part, okay, the first identity sequence of the selection is called out and the algorithm moves on below the selection instruction and implies stop in this case. And if the condition does not hold, okay, it means that the price is not greater than 5,000 pounds, okay. So the else part will be carried out, okay. And the second, it means that the second identity sequence of instructions, and then the algorithm moves and stop, okay. So the way the algorithm is set out with the condition at the top and the two sequences of instruction in the identity underneath emphasizes the connection between them, okay. So if it were not required to tell the user that no loyalty point were added, were awarded, sorry, when the total price is, the algorithm could not, could have been written using Simply the if instruction. Okay, if you don't need to communicate the user that he doesn't have, or he didn't have any loyalty, okay, you can use only the if. Okay, you don't need to use the if else. Okay, here because we need to tell the user that he don't have any loyalty. Okay, we will use, look here, because we need to tell the user that there is no loyalty points earned. Okay, we use the else. Once we don't need to tell the user this remark. Okay, so we only use the if clauses. If the total price is greater than 5,000 pounds, you will calculate the loyalty and tell the user there is a loyalty point earned. Okay. Okay, is it clear? Clear right now? Clear? I need your feedback. Okay. Okay, thank you. Okay. Okay. So in how you build, this selection can be implemented using the if clauses. Okay. So if the total price is greater than 5,000, then set the loyalty point to round 0.05 by the total price. Okay. Multiply by the total 5% of the total price, and say you have earned loyalty points. Okay. Else no loyalty points are applied. Okay. Okay. In Python, an equivalent code can be implemented using similar wording and indentations. So if the total price is greater than, than 5,000, okay, loyalty points will be equal round 0.05 multiplied by the total price, and the print you have earned loyalty points, okay. Else you will print no loyalty points earned. Okay, is it clear? Okay, now we deal with the sequential and nested selection. Now the nested selection, you remember the nested selection? What does it mean, the nested selection? What does it mean? What does it mean? Nested selection. I need your feedback. Forever block. Yeah, good, Sadia. No blocks run necessarily when you use the nested block. So block inside block, okay? Yeah, good. One block inside the block, okay? So we will have inner blocks or inner blocks and outer block, inner block and outer block, or inner selection and outer selection, inner repetition, outer repetition, etc. Okay, can be. Okay, So suppose I always provide for my children the same meal on the same day each week. Okay, as follows. So in the Monday, I will give my child meatloaf. In the Tuesday, shepherd pie. In the Wednesday, omelette. In the Thursday, chili. In the Friday, fish and chips. Okay. So I will create an algorithm, something like the following. So I will input the day. If the day is Monday, then set me to meatloaf. If the day is Tuesday, then etc. Okay, and I will output the meal at the end. Okay. In audio build, this may be implemented using sequence of selection instructions. We have seen already the sequence of selection instruction. Okay, and we see that here we have unnecessary blocks that will be run. Okay, for example, if we are in the on day, okay, I will set the meal to meatloaf, but I still compare if it is Tuesday, if it is Wednesday, if it is Thursday, if it is Friday. So all these instructions are unnecessary to run. Okay, when the day is Monday, it is the same when the day is Tuesday. I don't need to run all these instructions. Okay, so there are some unnecessary instructions that will be run. Okay, and that will be that will be evaluated. Okay, even when it is not necessary. Okay, in Python there are some as equivalent, okay, version. So if day is equal to m, meal equal to meatloaf, etc. Okay, but here the previous code will work perfectly, but it is not very elegant. It is not efficient. Okay, so whatever the day is input, the algorithm works its way through every one of the 5 if-then instructions. So a more elegant and a more efficient algorithm can be done using nested. Okay, do you remember the sequential and the nested selection already? When we see in the first time the nested, okay, we compare the nested structure with the sequential instruction, and we see that there are unnecessary runs of some instructions in the sequential structure. Okay, so the nested structure prevents the algorithm proceeding any further through the selection instructions once it has reached the condition, okay, corresponding to the given day. Okay, so this is the importance of the nested structure, of the nested selection here. Okay, so look now to the nested structure below. Input the day. If the day is Monday, then set the meal. Okay, so all this else will not be run. Okay, will be omitted, will be skipped. Else, if the Monday is not the right day, so I will go through the else. Okay, I will not go there. I will go through the else. In the else, I will compare if the day is Tuesday. If it is okay, I will set the meal to shepherd pies, and I will skip all this part, else I will go to the okay. So you can see now that there are no unnecessary blocks that will be run. Okay, no blocks run unnecessary. All the required blocks will be run. Okay, is it clear? Switch instruction now. Some other languages, though not Python, have a slightly neater way of dealing with such situations when you have several choices, known as case instructions or switch instructions. Okay, there are some case. Okay, you will use case. Okay, and other programming language you will use the switch. So which allow for several different courses of action to be taken according to the value of a variable, and thus avoid the need of complex combinations of selection instructions. So look now, when we use, for example, in Java, you can use the switch, okay? So switch day, if the case is Monday, okay, so you will print out the mail and you will break, okay, all this part will be omitted, okay. If it is Tuesday, so you need to enter the day from these cases, okay. So move now to the good algorithm. When we can say that is good algorithm, what does it mean, a good algorithm? When we say that it is a good algorithm, what do you think? What can be a good algorithm? What is a good algorithm? Tell me. Easy to understand. Okay, good. A clearer instruction. Okay, good. What else? Yeah, clearer, it means that it is ambiguous, okay? Not ambiguous. What else? Less complex, yeah, we can say that. Can be reused, yeah, can be reused, can be reused several times. Okay, clear, good. Okay, so one possibility is to measure the goodness of this algorithm in terms of which algorithms are easiest to understand. Okay, so when the algorithm is easy to understand, it means it is a good algorithm. Okay. A second idea to think, or if an algorithm is clear, so it can be easier to translate it into computer program and test it for correctness. Okay, so when it is clear, when it is easier to understand, okay, it can be translated easily, okay, into a computer program and tested, okay, for correctness. Okay. A second idea to think about is how much effort it will take to carry out each algorithm. Okay, so when we design an algorithm, we expect to use it many times. And so we want the algorithm to be efficient and not require more effort and time than necessary. Okay, so we need now an algorithm that it is easier, okay, to understand, that it is easier to implement. Okay, that does not require much effort, okay, to carry out this algorithm. So the first point is important. It is understandable algorithms result in more readable computer programs that are easier to maintain. Okay. The second point is not quite as straightforward to answer, so it may not be immediately apparent that two algorithms performing the same task can involve different amounts of effort. Okay. The following simple example shows how the choice of an algorithm can make a lot of difference. So look now. Suppose that you have 1,000 guests attend a feed, okay? So how many arithmetic operations would be required to calculate the cost of cupcakes by algorithm A and algorithm B? Okay, we have two algorithms that calculate the total cost, okay, of cupcake. So we can plot on a graph the number of arithmetic operation required by algorithm A, okay, and algorithm B with varying number of guests as showing in figure 5. Look now. So this is the algorithm A, okay, this is the algorithm B. As the number of guests, okay, increase, the number of operations increase, okay. So look at the algorithm B and algorithm A. What do you think? What do you think about algorithm A and algorithm B? What is the efficient algorithm? What is the good algorithm? And why? Turkey said that algorithm A is good. Why is good algorithm A? Tell me. Tell me, Ragad. Tell me, Saif, Turkey. Why algorithm A is good? Why? Ahmed and Saadia say that B is more efficient, and they see that the algorithm B uses less operations for more guests, so it will require, okay, less time, okay. So when you talk about algorithm, goodness of algorithm, you need to talk about the number of operations. You need to talk about the time achieved. You need to talk about the complexity. Okay. Here we think that, and we can see easily that algorithm B is less complex to algorithm A. Why? Because here, for example, 1000. We have, for algorithm B, we have only 100 operations, okay? But with algorithm A, we have 200 operations. We have the double of number of operations. So we have the double of time, okay? We have a double of memories, allocated memories, resources, okay? So we have already many expenses, okay? Many resources, as well as in terms of times, memory, okay, complexity, etc. So for both algorithm, the number of operations increases along with the number of guests. Okay, it is okay. Both of them will increase the number of operations as well as the number of guests increases. Okay. And both algorithms produce straight line on the graph between the number of operation and the number of guests. So it is a linear relationship, okay? But the algorithm A is inefficient since its line is steeper than for that, okay, than that for the algorithm B, showing that the number of operations required for algorithm A grows more rapidly as the number of gets increases. Okay, it will increases more rapidly than algorithm B. Okay, so it is inefficient. Okay, when it is compared with algorithm B. Okay, so this is what does it mean, a good algorithm. So a good algorithm need to be easy to understand, need to have, okay, we not expect to use it many times, okay, we need to use it many times, we need to make the choice, okay. When you have many, okay, algorithms, you need to make the choice of the efficient one, of the good one, okay, in terms of complexity, in terms of time, in terms of number of operations, okay, etc. Okay, is it clear now what is a good, how we can say that it is a good algorithm? Is it clear now or not? Clear? Okay. Okay. So move now to another thing, it is swapping now. So we will move now to the swapping. So swapping here means swapping two items of any kind is a fundamental activity that we perform in the real world, as well as being a key part of many algorithms, including those used to sort data. Okay. So swapping is used when you need to sort data. Okay. Sort data, it means to keep the data in such order. Increasing order, decreasing order, ascending, descending, okay, etc. So swapping is nothing more than exchanging position or positions, okay? So when you have item 1 in position A, when you have item 2 in position B, and you need to exchange item 1 in item 2, okay? Here and item 1 in the position of item 2. So this is what does it mean swapping, okay? Is it clear? What does it mean swapping? Clear? Okay. So let's write now a swapping algorithm. Specifically, you will write an algorithm that will swap the values of two variables. So to make the process simpler, we will present two variables using two post-it notes, okay, small pieces of paper. We label the first item 1 and the second item 2 as shown in this figure. So now write Bob on item 1 and Alice on item 2 as shown in this figure 7. The two post-it notes, item 1 and item 2, represent two variables. Okay, so this is the first variable, this is the second variable. Item 1 has the value of Bob, item 2 has the value of Alice. We need now to swap the values of item 1 and item 2. This can be done by the following algorithm. Okay, so set item 2 to item 1 and set item 1 to item 2. Okay, so this is one way to swap. Okay, but now applying this algorithm results in item 1 and item 2, both have the value now Bob as shown in figure 8. Okay, so how you can solve this? Okay, so look, now this is item 1, this is item 2. I will set item 2 to item 1, this is item 2. I will set item 2 to item 1, so it will be here Bob. Okay, are you okay? This is Bob. And set item 1 now to item 2. This is item 1. This is item 2, Bob. So I will write Bob here, okay? Again, okay? So I will have two items with Bob. Okay? So in fact, I don't do the swapping, okay? Because I already lost my item 2 Alice, okay? To solve the problem, we need to add a temporary variable. Okay, we need a temp variable as shown here. Why? To get Alice here, okay? Okay, here I will store Alice. This is Alice. So I will set temp to item 2. I will set item 2 to item 1. Okay, this is Bob. And I will set item 1 to temp. Okay, so this is Alice here. Okay, so this is the right way to do the swapping. Okay, this is Alice. Okay, are you okay? So the new algorithm follows the 3 steps in sequence. Copy the value of item 2 to temp. Copy the value of item 1 to item 2, and copy the value to temp of temp to item 1. And by this way, we will have the right swapping. Okay, so we can write now down this algorithm of instruction as an algorithm. Set temp to item 2, set item 2 to item 1, and set item 1 to temp. Okay, so this is the correct way to do swapping, and not this one, and not this one. Okay, this one cannot do the swapping in right form. Okay, so this one. Okay, are you okay? Are you with me? It is okay. Okay. Look now, this swap algorithm is a fundamental part of many more complex algorithms and can be found at the heart of almost all major systems, such as banking, stock markets, online shopping sites, etc. So this only 3 lines long, but it is a key part of the modern world. This algorithm is straightforward to implement in all you build as in figure 13. Okay, so we will define 3 variables. Okay, temp item 1 and temp 2. Item 2. We will set temp to item 2, set item 2 to item 1, and set item 1 to temp. Okay. In Python, it is the same thing. So we will define 3 variables, and we will assign item 2 to item to temp, item 1 to item 2, temp to item 1. Okay. So this is the swapping. So we saw that we need the swapping to the sorting. Okay, when you need to sort an area or an algorithm, a part, okay, a list or string or whatever. So sorting is an area where efficient algorithms are crucial, since it is one of the most common purpose, okay, for computers. You may have used sorting to recognize your emails or to rearrange data in spreadsheet, etc. Google sorts the results by usefulness, for example, etc. Okay. So sorting is found in spell checking in word processors, in compressing data so that it uses less disk space, in prioritizing tasks in the computers that control aircraft, industrial plants, power stations to ensure safety, in arranging on-screen objects from the most distant to the closest to ensure the graphics in 3D video games are drawn correctly, etc. Okay, so this is some of examples where sorting is found. Okay, so what does it mean, sorting? Sorting algorithms like take lists of unsorted data and turn them into lists of sorted data. Okay, so the input is unsorted data, the output will be sorted data. Okay, sorting simply is the process of putting similar items into order. For example, we can sort numbers in ascending order or descending order. Okay, we can sort words alphabetically or in inverse alphabetically order by length, frequency of use. We can sort events ordered by dates. We can sort items in an online shop by price, by popularity, and so on. Okay, so this is example of sorting. Okay, there are many types and many ways of sorting. Okay, look now at this list. Here is a short list of names sorted in alphabetical order. So here we have Ahmed, Basil, Marwan, Saif, and Ziad. You see here A, okay, the capital A, after that B, after that M, after that S and Z. Okay, so we can order now these names, okay, by alphabetically order of the first letter. Okay, so a list is made up of items of data, each living position in the list. The first item is at position 1, the second at position 2, and so on. Okay, so a list can be described in terms of its length. This list has length 5. Okay, so here we have 5, and so look now. Here is a list of place names. Okay, so give me this list sorted. Okay, give me what is the first one? Here is a list of places. Yes, and we need to order this list in, okay, alphabetically letter. Okay, so in the first it is Byblos, second Cairo, okay, third Dubai, okay, fourth Istanbul, fifth Jerusalem, okay, Jerusalem, okay, Petra, 6 and 7 Salalah, okay. So this is in the right order, okay. So is the list, this list is sorted? No, this list is not sorted. Okay, it appears that it is not sorted. And what is the length of this list? The length of this list is 7. Okay. Okay, good. And what is the item at position 6? What is the item now at the position 6? The item? The item at position 6. So this is position 1, 2, 3, 4, 5, 6. Byblos, good. And what is the position of Petra in the list now? The position of Petra? 1, 2, 3, 4, 5. Position 5. Okay. So this is one list. And when we sorted, okay, so we have already sorted. Okay, good. So selection sort now. So there are many types of sort. Okay. So there are selection sort. There are the bubble sort. Okay, and the merge sort. Okay. We see all these type of sort. Okay. So let's begin by the selection sort now. So this algorithm repeatedly searches for the smallest or lowest item in a list of unsorted data and moves the item to the end of a list of sorted data. Okay, so do you understand how the selection sort works? Okay, look now, we will search to the smallest or the lowest. Okay, and we will move this item to the end of the list. Okay. So the algorithm repeats until all the data is sorted. The selection sort can be implemented using two separate lists. Okay, we can have two separate lists, one for unsorted data and the other for the sorted data. Such algorithms are called not in place sorts because we have two lists, but they are not often used in computer programs because there is a more elegant way to sort using a single list, okay, containing both sorted and unsorted portions. Okay, so we can now we can use the same list. Okay, it is not efficient to use two lists because it will it will use more resources, it will allocate more memories. Okay, so there are some expense, okay, of these algorithms. So we need what? We need algorithms that use the same list. Okay, so because we will use the same list, so here all the algorithm source items within the original list are known as in-place sort. Okay, so there are two types: not in-place sorts and in-place sort. Okay, the not in-place sort is not often used in a computer program because there are many resources that will be used. Okay, and gasped. Okay. So look now, the algorithm for the in-place selection sorts can be written as follows. So this is the selection sort. I will repeat until only one item of insorted data remains. Okay, so I will find the lowest and I will swap. So here we talk about the in-place. Okay, we have only one. And I will swap the lowest item with the first item in the unsorted data. Okay. I will do here permutation, exchanging, swapping. So how does it work? I will search through the list and find the smallest element. I will swap the smallest element with the first element or the last element, okay? And I will repeat starting at second element and find the smallest one. So look now, this is my list. So I will scan items from 1 to 5. 1, 2, 3, 4, 5. I will get, or I will calculate the smallest. The smallest is 20, okay? I will swap 20 and the first item. So this is my new list. 20 at the first place. The others are the same order, okay? Just I will swap 20 with the first item, okay? So this is my list now, okay? After the first iteration. After that, I will scan items from here to 5. I will calculate the smallest item, okay? It will be here 30. And I will exchange the 30 by 65, okay? This is 65, this is 30, and we will exchange, okay? So I will have 20, 30, 65, 60, and 35, okay? So this is my new list. Okay, is it clear? Is it clear? After that, we will start by 65 to 33 and 5, okay? And we will compute the smallest. This is the smallest. We will exchange or swapping the smallest with 65, okay? After that, we will scan the items from 4 to 5, okay? And we will use so 60 is okay, so we will swap the smallest with the item number 4, okay, and we will have the list sorted, okay? So by this way, at the end, okay, we will have the list sorted, okay? Is it clear? What is the selection sort? Clear the selection sort? Clear? So this is the selection sort, okay? Of in place, okay? In place sort, okay? It is not in place, okay? So we will use the same list. We will make order with the same list, okay? Just we will search for the smallest item and we will exchange, okay? We will do swapping between the smallest item and the first item, okay? Of the list, okay? Okay. Now at the bubble sort now, another type of sort. So like sort, like selection sort, the bubble sort is based on comparisons, okay? It will be comparisons, but now the comparisons bubble sort works methodically, okay? Through a list from beginning to end, comparing each pair of adjacent items, okay? Now we will not go through all the list and find the smallest and do some swapping, okay, by the smallest and the first item. Now we will compare just the adjacent. So if the two items are in the wrong order, they are swapped. The algorithm then moves one position along the list and compares the next pairs and so on. And we can write the part of the algorithm that passes from the beginning to the end of the list swapping. Okay, so swapping adjacent item if they are not in order, like this. Okay, so swapping pass, starting at the beginning of the list. Repeat for each pair of adjacent items. If the items are in the wrong order, then swap them. Okay. Okay. So here are three lists sorted using the swapping pass algorithm we have developed so far. So what characteristic do the list item in each of the sorted lists share? Okay. So look here. This is the list before swapping pass, and this is the list after swapping pass. So look here. I will compare Marwan and Ziad, okay? So Marwan and Ziad in the right order, okay? I will not do any swapping. I will move now to the next pair. I will compare Ziad and Basil. Ziad and Basil is not in the right order, so I will swap Ziad and Basil. So I will have Marwan, Basil, after that Ziad, okay? I will now compare the next pair. The next pair will be here, Ziad and Ahmed. Ziad and Ahmed is not in the same order, in the right order, so I will swap Ziad and Ahmed. So here I will have Basil, here I will have Ahmed, here I will have Ziad. I will compare Ziad and Saif, and I will have this one. Okay, this is the what? The output of this algorithm, of this swapping pass algorithm that we have applied. Okay, so as you can see here, it is after the swapping pass, it is good. We have a good ordered list or not? What do you think? It's lagging, yeah. Huh? You don't see the here the slide? I think it is because the connection, internet connection in the campus is not very good. Yeah, because it is some lagging because of the internet connection. Okay, so as you can see here, I don't have a good order. Okay, so here Ahmed, okay, not in the right form. Look now for the 22, 4, 7, 10, and 3. Okay, so I will compare 22 and 4. I will have here 4 and here 22. Okay, I will compare 22 with 7, so I will have here 7. Okay, 7, and here 22. 22 with 100. Okay, 103. So I will have 3. So 4, 7, 22, 3, and 100. So it is not a good order. Okay, it is partially ordered. It is the same thing for this list. So our list here is now partially ordered after one swapping pass. So the last item is always in the correctly sorted position. However, the remainder of the list needs further sorting. So as you can see here, the last item is okay. Okay, only for the last item. Okay, Salela. Okay, 100. Okay, Ziad. It is the last. But I need more iterations, okay? More generally, a list that containing n items will be sorted after n-1 swapping passes through it. So we can create an algorithm to completely sort a list by nesting the swapping pass inside the loop as follows. The bubble sort. I will repeat the length of the list -1 times. Starting at the beginning of the list, repeat for each pair of adjacent items. If the items are in the wrong order, then swap item, okay? So it will have, this is the swapping pass, and I will repeat this swapping pass n-1 times. Okay, so look at this example now. Move from to the end. So the bubble, the largest value of it to the end using the pairwise comparison and swapping. Look now. So I will do the first, okay, iteration. So I will compare 77 and 42. Okay, 42 is lower, so it will be swapped. Okay, there will be swapped. After that, I will compare 77 and 35. Okay, 77 is greater than 35, it will be swap. Okay, I will compare 77 and 12. Okay, swap. I will compare 77 and 101, so there is no swapping here because this number is greater. I will compare the 101 and 5, so it will be swapped. So by this, in the first iteration, I am sure that the biggest one will be at the end. Okay, so now I will, so the largest value collected, placed. Now I will now do the same thing. Okay, so notice that only the largest value is correctly placed, all other values still out of order. So we need to repeat this process. If we have n elements in each time we bubble an element, so we place it in its order. So we will repeat the bubble up n-1 times. This guarantees we will correctly place all n elements. Okay, so look now. We will, after the second iteration, the 77 will be in the right place. After the third iteration, the 42 will be in the right place. After the fourth iteration, the 35, and after the fourth iteration, this is n-1. So how much here? We have 6 elements. So we need 5 iterations. 1, 2, 3, 4, 5 iterations to have the right order. Okay, is it clear? Are you with me? So this is the bubble sort. Okay, move now to the merge sort. So the merge sort is a very popular way of sorting data, not only because it is much faster than bubble sort for most purposes, but also because it can be designed to work on parallel processing computers in which each processor performs part of the sort. So table 1 shows generally how much longer it takes to sort a list using bubble sort than using merge sort, assuming they are both using the same unsorted data and implemented in the same computer hardware. Okay, so look now here. Look now the number of items to be sorted here, 10. Okay, and the ratio of bubble sort to merge sorts is equal to 10. Okay, so we need 10 times, okay, number of operations needed to do the bubble sort, okay, compared with the merge sort, okay. So here, whilst most of us do not need to sort much volumes of data, sorting millions or even billions of items is commonplace in large organizations, okay. So you can see here, when you have only 100 items to be sorted, so you need 50 more operations to do in bubble sort comparing with merge sort, okay, etc. So as you can see from this table, it is increasingly advantageous to use merge sort as the number of items to be sorted increases, okay. So if you have 100 items to sort, merge sort on average sorts the item 50 times faster than the bubble sort. Whilst if you have 1,000,000 items, it is nearly 164,000 times faster. Okay, so you see how it is fast. Okay, why? Because the number of operations is less. Okay, is lower. Okay, so this is why it will be more faster, or it will be faster. Okay, than the selection sort, okay, the bubble sort, okay. So you see that we have 3 types of sort: the selection sort, the bubble sort, and the merge sort. And we see that the merge sort is the very popular way and the faster way, okay, to do sorting, okay. So having completed this part, you should be able to describe what an algorithm is and provide everyday examples, okay? Describe the fundamental building blocks of algorithm. Match parts of a small programming language such as Python or Java to parts of an algorithm. Use visual aids such as pieces of paper to follow an algorithm. Learn different type of sorting algorithms and apply a sorting algorithm to particular list. Okay, so we will see that tomorrow. We will apply these sorting algorithms tomorrow, inshallah. So do you have any question? This is all about meeting 6, tutorial 6, okay? So if you have any question, you are welcome. Do you have any question? Is it clear? Thank you, Sadia, thank you. Thank you, okay. Thank you very much for your attendance, for your interactions.